So far, we have only looked at the forward process of the transformer network encoder, assuming that we already have trained parameters that lead to meaningful token representations that come out of the encoder. In this video, I will show you how we can train transformer network encoders to actually produce meaningful numerical representations of the input sequences. Let's have a look at which parameters are actually trainable. So what can we adjust during model training to achieve better representations? Let's assume for now that for the input embeddings and the positional encodings, we have predefined methods, which would mean that we don't have any learnable parameters in this part of the encoder. An alternative would be to learn the embeddings during training, which would give us learnable parameters. But to keep it as simple as possible for now, let's say we use predefined methods that give us useful input embeddings and positional encodings. Then we have the attention block. We have seen that in each head of the multi-head attention function, we have matrices WE, WK, and WV. And all entries of these matrices can be adjusted during training. And also the matrix WO that we use to transform the concatenated vector has adjustable parameters. Then we have layer normalization, where we have the learnable parameters gamma and beta, and those parameters allow us to rescale the normalized embeddings. And finally, we have the fully connected neural network, where we again have matrices W1 and W2 with trainable entries, and also bias vectors B1 and B2 with adjustable entries. And then we have again learnable gamma and beta parameters in the layer normalization following the feed-forward block. And of course, we have different sets of all of these red parameters that you see on this slide in each layer of the transformer network encoder. Before we actually train the encoder network, we have to set the learnable parameters to some initial starting values. And typically, the bias vectors B are set to 0, and the entries of the matrices W are typically set to small Gaussian distributed values that are distributed around 0. And for the parameters of the layer normalization, you would typically set all entries of gamma to 1 and all entries of beta to 0. This means that applying beta and gamma to your functions is initially not changing anything, and those functions are basically identical to the identity function. Now let us look at how we can train the transformer network encoder to find useful parameters. We remember what our encoder does when we input a protein amino acid sequence. The sequence is divided into tokens, where each token is an amino acid of our input sequence. And the encoder then processes this sequence and outputs a numerical representation for each amino acid. If we want to train the encoder in a self-supervised way, we can train it for the following task. We can randomly mask some of the amino acids in the input sequence, let's say about 15% of all amino acids. This means that, for example, that we do not let the model know what type of amino acid we have in the third position. How we do this is we add an additional token to our model, the so-called mask token. So far, we have 20 different tokens for all the amino acids that we can have in a sequence. So we have to add a 21st token that tells the model that we don't know what the amino acid is at that position. We then train the model to predict what type of amino acid we have at the masked positions. To do this, we can, for example, train a single layer neural network on top of the corresponding token representation, which outputs a vector with 20 entries, where each entry corresponds to one amino acid. For example, the first entry might correspond to the amino acid alanine, the second to leucine, and the last to valine. To this vector, we can apply the softmax function, and we already know from the attention function that this results in a vector with values between 0 and 1 that sum up to 1. So for each amino acid, we get a score between 0 and 1 that indicates how likely it is that we have a certain amino acid at that position, where values closer to 1 indicate that it is more likely that we have this amino acid at that position. In this case, for example, we could get a high score for K, which represents leucine, which is actually the true amino acid at that position. So how do we train the model to predict the correct amino acid for the masked positions? For all the masked positions, we can create a binary vector with all zeros and a single one, indicating the true amino acid at that position. We then compute the vector y we compare the vector y of the true amino acid, which is the vector we want to predict, with the vector y hat containing the predictions of our encoder. We now calculate the value of a loss function, which tells us how far away are we from the desired prediction. Typically, we compute the categorical cross-entropy loss, defined as shown here. For all 20 entries of the resulting vector y, we compute the product of yi with the logarithm of yi hat. Since only one entry in our vector y is non-zero, the entire sum will simply be a single multiplication of yi with the logarithm of the value we predicted for the true class. So in our case, we get -1 times the logarithm of the predicted value for the second amino acid, which is 0.57. If we look at the values of the logarithm between 0 and 1, we see that for values close to 0, we get very negative values. And since we have a minus sign in front of the logarithm, this means that we get a very high loss. This makes sense because we want to predict a high value close to 1 for the true amino acid. And we see that when we do that, when we predict a value close to 1, the value of the logarithm is close to 0 and we have a very small loss. As you probably know, we apply the encoder during training typically not only to one sequence, but to multiple sequences at once that are part of a mini batch. In this case, we simply calculate the average categorical cross-entropy across the batch and across all the masked positions in these sequences. And during training, we would process a batch, compute this average loss, and then compute the gradient of this loss function with respect to each learnable parameter. The gradient now tells us how to change each parameter a little bit so that the loss decreases slightly. So we take a small step in that direction. And then we would process another batch and repeat this process. And we will now look at the next slide at this process in a little bit more detail. On the previous slide, we have seen that this is the formula for calculating the loss for a single masked token. If we process a batch consisting of multiple sequences, where in each sequence we have multiple masked tokens, we can calculate the loss for this whole batch by simply calculating the average over the loss of all m masked tokens. So this value tells you how well you're doing on average for predicting the type of masked tokens on your batch that you have processed. We can now use backpropagation to update all learnable parameters based on this calculated loss. What I'm going to say now is basically true for the training of any deep artificial neural network. So what we do is we calculate the gradient of the loss function towards every adjustable or learnable parameter in our transformer network using backpropagation. This means we calculate the gradient with respect to all single parameters in all matrices W, with respect to the entries of the bias vectors B, and with respect to the parameters gamma and beta that are part of the layer normalizations. And for simplicity, we denote every learnable parameter here by a lowercase w. This gives us, for each parameter w in our transformer network, a single value, and we know that if we move a little bit in the direction of the negative gradient of the loss function, we reduce the loss function a little bit. which is what we want to actually achieve. So this is what we do for each parameter. We update each parameter by moving a little bit in the direction of the negative gradient of the loss function with respect to this parameter. And how much we move in the direction of the negative gradient is defined by the learning rate, which is denoted here by LR. And after doing this for all parameters, we will process the next batch in the training process and again update all learnable parameters following this procedure. And this is done over and over again. This training approach is called self-supervised training because the model uses the input data itself to generate the data for the training task, and it does not require any external data to be labeled or measured. But why is this self-supervised training, where we randomly masked 15% of the amino acids in the input sequence, a good approach to generate better or more meaningful representations of the amino acids in our sequence? To successfully solve this task of predicting the type of a masked amino acid, the model must extract information from the other amino acids in the sequence. In doing so, the model learns the context in which the amino acids are located, and it also learns the dependencies between these amino acids, which is critical to understand protein structure and function. And although we trained the model directly only to generate useful representations for the masked tokens that we can then use for predicting the type of amino acid, to accomplish this task, the model must also generate informative representations of the other tokens so that we can easily extract information from them when we try to gather useful information about the masked token. This means that if after training we apply a protein amino acid sequence that is not masked to the trained encoder, we will still get useful and informative representations of all the amino acids in the protein sequence. And these representations contain not only information about the amino acid itself and its position in the sequence, but also about its context in the sequence and its dependencies with other amino acids. In the next video, we will see that by learning to predict masked amino acids within a sequence, the model also implicitly learns about the structural and functional properties of proteins. When we want to develop a model to predict the property of a protein, we can use the protein encoder that was trained for the masked token prediction task. When developing a prediction model for a protein property or function prediction task, we usually need a single vector of a fixed size for all proteins in our dataset, even if we have proteins with different protein sequence length. However, when we apply our transformer network, we get one d-dimensional numerical representation for each amino acid in the input sequence, so the number of vectors depend on the length of the input sequence. As we have already discussed before, to obtain a single vector of fixed dimension for the entire protein sequence, we can compute the element-wise mean of all amino acid representations. This results in a single vector of dimension d for all proteins. Calculating the element-wise mean means that we calculate the mean of all the first entries of all representations and use this value as the first entry of our new vector. Then we calculate the mean of the second entries of all vectors and use this as the second entry of the new vector, and so on. And this whole protein representation is calculated after model training, and we present the whole amino acid sequence to the model without any masking. And it may seem surprising that computing the element-wise mean of all amino acid vectors results in a useful protein representation. But each representation contains not only information about the amino acid itself, but also contextual information. And by averaging these vectors, we aggregate the contextual information over the entire sequence, resulting in a representation that reflects the overall properties. However, you still may wonder if this does not result in a loss of information, and indeed, to a certain amount, this averaging does result in loss of information. Specific details about the sequence, such as the exact order of amino acids, local patterns, or the presence of specific motifs and domains, are not explicitly captured in the average representation. However, despite this loss of detailed information, averaged representations can still be effective for many applications, for prediction tasks that require the understanding of general protein properties such as their overall function, family classification, or properties that are distributed across the entire sequence. To overcome the limitation that this representation is only a very general protein representation that may not capture all the necessary information that we need for a specific prediction task, we will see later that we can also train a protein sequence encoder on a specific task in a supervised fashion that directly results in a single vector that contains all the relevant information needed to solve a particular prediction task.